Hello student. Today we will discuss about McCabe-Thiele method in distillation column. So what is the purpose of McCabe-Thiele method? McCabe-Thiele method is used for to calculate required number of ideal stages to achieve the desired separation. For identifying the number of ideal stages, required number of ideal stages to achieve the desired separation. Student, always remember it is the ideal stage. It is the ideal stages, not trait. Keep in your mind. It is the ideal stages, not trait. So it will give you an idea about ideal stages, not trait. So just look here, this diagrams XY diagram. It is also known as equilibrium diagram. So what is X? X is a mole fraction of more volatile component in liquid state. Y, what is Y? Y is the mole fraction of more volatile component in vapor state. So 0, 0.2, 0.4, 0.6, 0.81. This is a mole fraction of Y. Similarly, 0, 0.2, 0.4, 0.6, 0.81. It is a mole fraction of X. It is Y is equal to X. It is diagonal. It is the equilibrium curve between Y and X. It is the equilibrium curve between Y and X. Sometime in problem it is given that X and Y, you have to draw the equilibrium curve. Suppose some value is given here, you have to put the value of X and Y and you will get this graph. So for calculating the number of ideal stages, what you need? You need operating line equation. Operating line equation for rectifying section. In my previous video, I have already told you the equation of operating line for rectifying section. It is a y is equal to r divided by r plus 1 into x plus xd divided by r plus 1. So when you will put the value of y is equal to x here, you will get xd. Like x is equal to xd, y is equal to xd. So you will get this value. So suppose in the problem it is given that you have some value of composition of top product xd, more volatile component having composition xd, and in the bottom product you have a composition of xw. XW. It is XW. What is XW? It is a composition of more volatile component in bottom product, or you can say it is a mole fraction of what mole fraction of more volatile component in bottom product. So before comes to a solution, we have to understand what is feed line equation. What is, suppose you are just feeding some feed in a distillation column. This feed which you are feeding in a distillation column, it may be saturated liquid, it may be subcooled liquid, it may be liquid and vapor mixture, it may be saturated vapor, or it may be superheated vapor. So when you will draw the graph, suppose you will draw feed line, y and x equilibrium curve. When you line feed line q line, we have already studied q line. So feed line, what is feed line? When saturated liquid is when feed your saturated liquid, you will get the feed line like this. When you have subcooled liquid, you will get feed line like this. When you have a liquid and vapor mixture, you will get feed line like this. When you have a saturated vapor, then you will get feed line parallel to x-axis. When you have superheated vapor, then you will get q line like this, feed line. So suppose in this question we have a saturated liquid. So our feed line equation will like this, and we already know that in the problem it is given xd composition and xw composition. So just put the value of xd xd here and xw xw here. So you have a 1 point, and you know that y is equal to r plus 1 r plus 1 into x plus xd r plus 1. What is xd r plus 1? It is an intercept. Y is equal to mx plus c. It is a c. It is an intercept. xd divided by r plus 1. It is an intercept. So now we will draw operating line for rectifying section. Suppose xdr plus 1, it is intercept in on point 3. We have an intercept point 3. So just meet these 2 points. Just meet these 2 points like this. So when you will meet this point, you will get this line xd. It is a xdr plus 1 intercept. It is the operating line. It is the operating line for rectifying section. It is feed line, q line. You also know the q line. Suppose your feed is saturated liquid. So you will get this line. So you will now get this point. For operating line stripping section, you have to meet this xw point to this point. This point. Now, for getting the number of ideal stages, you have to just meet this point, and you parallel to x-axis. It will meet on the equilibrium curve. Then drag again straight line. Again on from operating line, you have to meet this point to equilibrium curve. Suppose this point you will get on equilibrium curve. Now just move down. Now again just move towards equilibrium curve. Now again on the operating line. Now move straight to equilibrium curve. Now move down. So you will end here. So you will get one tray, second tray, third tray, fourth tray. So or you can say you are getting 1, 2, 3, 4 stages. So now if your reboiler and condenser is total reboiler and total condenser, case first, if your reboiler and condenser is total reboiler and your condenser is total condenser, what it means? Suppose 100 kg liquid mixture comes and it will convert into 100 kg vapor, so it is a total condenser. Oh sorry, total reboiler. And 100 kg vapor comes in a condenser, it will converted it to 100 kg liquid, so it is a total condenser. So total reboiler, total condenser will never act as a ideal stage, because there is a no separation. They are not playing a part in a separation process. So in case first, number of ideal ideal tray will remain 4. In case first, when total reboiler, total condenser, your number of ideal stages equal to number of ideal tray, which is 4. In case second, when you are using partial reboiler and total condenser, now your partial reboiler will act as a stage, because partial reboiler, so it will plays some role in the separation process. So now, now your partial reviral will act as a ideal stage, one ideal stage. So number of ideal tray in a second case, number of ideal tray in a second case. This is a second case. It will be 3, 3, and but the number of ideal stage will remain same 4, because number of ideal tray 3 and your partial reviral will act as a fourth stage. But the number of ideal tray will be 3 in case in second case. In case third, in case third, when you are using partial reviler and partial condenser, then they both act as a ideal stage. They both act as a, so number of ideal tray will be 2 in third case. The number of ideal stages remains same 4 in second, first, third. Number of ideal stages will remain same, but in case of total revival, total condenser, number of ideal tray 4. In the second case, when you are using partial revival and total condenser, so number of ideal tray will be 3. In third case, when you are using partial revival and partial condenser, the number of ideal tray will be 2. Okay, hope this is clear. If you have any doubt, then just put in a comment. Okay, okay, hope it is clear, all of you.